Welcome everyone once again to geometry. We're going to continue taking a look at section 3, which is all about polygons. So we left off last time right at an activity. So that is where we are going to pick up today. All right. So the last time we started taking a look at this activity, saying that when we have a geometric figure, or sorry, when we have a polygon, the straight or the line segments of a polygon form sides or are the sides, and so we want to consider how many sides are in the polygon and look at those sorts of things. So we can have a polygon with 3 sides, as we saw last time. That's a triangle, and right, this is just a generic triangle. And we gave a theorem that stated that the angle sum, right, the sum of the angles of the triangle, the interior angles is what we can call them, is 180 degrees. And here it gives the number of interior triangles. And at first that kind of doesn't make sense, right? This is a triangle, so there's one triangle inside the triangle, and it's just the triangle itself. So that's nothing too crazy. But if we were to consider a 4-sided polygon, which in its most generic sense is called a quadrilateral. That could be anything with 4 sides. So a quadrilateral could look like, let's say, it looks like this. So it's not a square, it's not a rectangle. In this case, although squares and rectangles are quadrilaterals, they have 4 sides, certainly. But what we can do is we could split this up so that way this creates a number of triangles. So if we were to do that, find the number of interior triangles, we want to have triangles that whose vertices, the points that make up the triangle, be the same points that are in the actual quadrilateral. So the points of the triangle could only be these 1, 2, 3, 4 possible points. So let's say we split our quadrilateral like that. So now we have this triangle and this triangle. So there are 2 interior triangles. With that, we can use these triangles to find the sum of the interior angles. So if we wanted to find the sum of the 1, 2, 3, 4 angles of the quadrilateral, that would be finding the same thing as finding the sum of the 1, 2, 3, this half angle, 4, that half angle, 5, 6 angles of the 2 triangles, right? So if we add up those 6 angles, we would get the sum of the 4 angles from the single quadrilateral. But of course, we know that the sum of the angles in a triangle is 180 degrees. So we have 180 degrees contributing from this triangle and 180 degrees contributing from this triangle. So we get a total of 180 plus 180, or 360 degrees. So again, this angle plus this angle gives us the quadrilateral angle. And this angle plus this angle gives us the quadrilateral angle. So the sum of the 1, 2, 3, 4, 5, 6 triangle angles gives us the sum of the 1, 2, 3, 4 quadrilateral angles. All right, so we can keep doing this. So if we move on to a polygon with 5 sides, that's something that looks like this. And of course, that's a pentagon. And we can split this up into triangles as well. Again, we want the vertices of the triangle, or the points, corners of the triangle, to only be those of the 5-sided figure as well, which is called a pentagon. So let's see here. I can draw a line right here, and if I do that, that gives us a triangle on the left-hand side, and on the right-hand side, it's a quadrilateral, right? If you take this green side as substituting for those two blue sides, then this figure through here is a quadrilateral. And I can draw one line to split that quadrilateral into two triangles, giving us that for the pentagon, there are 1, 2, 3 interior triangles. And then the sum of those angles, right? If I wanted to add this one, plus this one, this one, this one, and that one, the 5 angles, I would be able to find that sum by adding up the angles of the triangles. And of course, the triangle has a sum of 300, or sum of 180. So 1, 2, 3, 1, 2, 3 triangles to give us, let's see here, that would be 540 degrees. Excellent. So we can continue on. We'll do the 6-sided figure together. And then I'll leave the 7 and 8-sided figure for you guys to work on yourselves. So the 6-sided figure is called a hexagon. And of course, that is going to look something like this. And we can split this into triangles as well. If I draw a line here, that gives me a triangle on the left-hand side and a pentagon on the right-hand side. And the pentagon I already split up, so I could split the pentagon up in the same way. Excellent. So my hexagon has been split into 1, 2, 3, 4 triangles. Again, these triangles have vertices which are the same vertices of the hexagon, and there are 4 triangles. So adding up the interior angles of the hexagon is the same as adding up the interior angles of the 4 triangles. And that would give us 4 times 180, which would be 720 degrees. And again, these last two, I leave for you. Excellent. So hopefully you've noticed a pattern which would allow us to identify the sum of the interior angles based on the number of sides. So of course there might not be necessarily a pattern. Well, there is a pattern to the names for the most part, but of course the figures themselves can be drawn many different ways, but there is definitely a pattern as to the number of interior triangles, interior triangles, and then the sum of the interior angles. And that pattern in particular, you can observe to be n minus 2 for an n-sided polygon times 180 degrees. That is the sum of the interior angles. Excellent. If you didn't notice that, we can return here and see that 3 sides has 1 interior triangle whose sum is 180 degrees. We're given that. But then what we notice is when we have 4 sides, we have 2 triangles, and 2 times 180 gives us our 360. So the number of sides minus 2 gives us the number of interior triangles, and the number of interior triangles times the times 180 gives us our sum of interior angles. 6 minus 2 is 4. 4 times 180 is 720. Excellent. And this indicates the end of a proof, so I'm not quite sure why that was there, but we could prove this, using mathematical induction. But notice in this case, our base case wouldn't be for n equals 1 because there is not a polygon with one side, nor a polygon with two sides. So our base case would be we're working with n greater than or equal to 3. So keep that in mind. All right, so a convex polygon is a polygon with a particular property. That property is that if A and B are points in an interior of the polygon, then the line segment connecting those 2 points is also, or is contained in the interior of the polygon. Excellent. So all triangles are convex, but any polygon with more than 3 sides, so 4 or more sides, does have examples that are not convex. So let's draw a few examples here. So for a 4-sided figure, we actually drew one already. Here's a 4-sided figure that is not convex. So for example, if I chose 2 points, one being here and one being here, if I wanted to draw the line between them, it would cross to the exterior and then back in. For a 5-sided figure, I could consider, much like I drew earlier, the house, but instead of having the peak go up, I can dip down inside. So again, if I were to take 2 points, inside, the line that connects them, the line segment that connects them, would go outside and then back in. So when we talk about the interior of a polygon, we're talking about inside the polygon. What's inside versus outside. And then, of course, there's lots of ways that we could do a 6-sided figure that is not convex. So we could do something like 1, 2, 3, 4, 5, 6. There we go. But we could also do something that looks like 1, 2, 3, 4, 5, 6. Okay, so lots of options there for a 6-sided figure. And as you get more and more sides, the more variation you can get in your non-convex examples. Excellent. So we looked earlier at a polygon that had, or wasn't a polygon, it was a non-example where the sides extended out. And we want to actually use that idea of having the sides extended out. So if we consider a triangle here, a polygon with 3 sides, if we were to extend those at each vertex, if we were to extend one of the sides, that would give us a new collection of angles, right? So angle 1, angle 2, angle 3. And these are called exterior angles of a polygon. They could have been done a little bit differently, and that would be all right. Notice that if we would have extended side 2 instead and labeled this as 3, right, because you have a straight line, right, this is always going to be 180 degrees. So if you're looking at that side that's less than 180 degrees, now what we have here are vertical angles, and these angle measures are the same. So calling this 3 or that 3 would be the same thing essentially, but that would give us an exterior angle either way. All right. So if we restrict ourselves to convex polygons for this conversation, then this theorem is a little bit easier to talk about. So this theorem, it gives the sum of the exterior angles for a polygon. And again, we'll look at a proof where it's just convex. But this actually holds for convex or non-convex polygons. So the sum of the measures of the exterior angles, one at each vertex, of a convex n-gon is, let's see, is 360 degrees. So it actually says that they have to be convex. I didn't catch that at first. So we'd have to look a little bit further for the non-convex. Although maybe that's just a little bit interesting because maybe we wouldn't have a good definition for an exterior angle. So let's simply say that we're talking about convex polygons. That way we can easily get an exterior angle each time. So no worries there. So if we wanted to consider or look at the proof that the sum of the angles is 360 degrees, what we would want to do is we would want to first consider the generic n-gon. So if I were to look at an n-gon, let's create a nice picture here. Let's see, go that way, and this way. Get a couple more, sorry, there, and here. And then because I don't have a specific number of sides, I'm going to use ellipses to indicate that it continues on, right? There's an unknown number of sides. And in particular, we have exterior angle n. We can label them with numbers. So let's label them as n is the end of it, but we start off at 1, 2, 3, and they continue on all the way up to n. Now I included n first because I want to have the end point. I have the beginning and I have the end. What's in between, I'm not quite sure about because that depends on n. So if I were to label my exterior angles in this way, I could label my interior angles with primes. So let's label our interior angles as n prime, 1 prime, 2 prime, 3 prime, and so on. Okay, 1 prime, 2 prime, 3 prime, on and on and on until you get to n. Excellent. So here we have a generic n-gon. Then let j be a number between 1 and n. Right, so we can refer to the angles. Then for each j, 1, 2, 3, 4, all the way up to n, for each j, the angle j and the angle j prime form a linear pair. We can see that, right, this side here is extended, so we get this angle and this angle form a linear pair because their non-common side, their non-common sides lay within the same line. Excellent. So each exterior angle and associated interior angle form a linear pair. That allows us to find a way to express the exterior angle in terms of the interior angle. So the measure of angle J can be given as 180 degrees minus the measure of angle J prime. So the exterior angle can be given as 180 degrees minus the measure of the interior angle, right? This is 180 degrees, and if I subtract the interior angle, that gives me the exterior angle. So this angle measure is 180 minus that one. That's what we have here. Therefore, we can say that the measure of angle 1 plus the measure of angle 2 plus all the way up to the measure of angle n can be rewritten as 180 degrees minus the measure of angle 1 prime plus 180 degrees minus the measure of angle 2 prime plus all the way up to 180 degrees minus the measure of angle n prime. Excellent. So what we can do is we can start to combine terms. So 180, 180, there are n of them, so n times 180 degrees minus the measure of angle 1 prime minus the measure of angle 2 prime minus all the way down to the measure of angle n prime. All right. Now we can pull out all the subtractions to get that this is n times 180 degrees minus the sum of all of the interior angles. And the sum of the interior angles we actually know. So we have n times 180 degrees minus n minus 2 times 180 degrees. We discussed that earlier. That's a proof that we already talked about, or a theorem that we already talked about. So here, this is equal to n times 180 minus n times 180 plus 2 times 180 degrees in each case. Of course, these cancel out, leaving us just with 360 degrees, which is what we wanted to show. We wanted to prove that the sum of the exterior angles is 180 degrees. Excellent. A regular polygon is a polygon in which each side is the same length and each interior angle has the same measure. So all of the side lengths are the same on this hexagon, and all of the interior angle measures are the same. So a regular polygon is typically what you think of for polygons. Excellent. And that's the end of the section. So if you have any questions about polygons, just go ahead and let me know. Send me an email, get a hold of me, set up an appointment so we can talk about it. And otherwise, the homeworks are posted online. So I'll see you guys soon. Have a wonderful day.